architectures. We learned about how to treat text data, how to treat time series, how to deal with basic neural nets, RNNs, CNNs. But the main question here is that how can we make this responsible? How can we present in a responsible way? Okay? And a responsibility, we may point this out many times today, has many different principles. It's not only about, as you will see, explainability. It's not only about, okay, the machine is making or the system is making a decision. Is this decision fair? Is this decision understandable? There are other issues too, like with the data. You are working with the data. There are certain biases in the attributes, for example. Do you favor more attributes than others? Do you make a decision towards, let's say, a particular race or a particular gender? So all of these things are actually within something we call responsible AI, and of course, responsible AI is not only about deep neural networks. We will present it through a deep neural network framework, because this is a deep neural network workshop. But if you make decisions, let's say, using a logistic regression model, the same questions apply to you. Is this fair? Is it explainable? Is it green? Is it, fair? And so on. Okay? Why? And we're going to start with one of the most important principles, explainability. Why explainability matters? Okay? So they are very powerful. These neural networks are very powerful. You already have realized, that when you are using neural networks, you will be able to get very high predictions. Okay? You hyperparameter tune, and you are getting high predictions, very good predictions. The first question is, why did the model make a particular prediction? Again and again, we're going to say that this is something called local explainability. You are interested in a particular document, and the model is making a particular prediction. You should answer immediately, or find a way, a mechanism to answer why the model that you have developed makes such a prediction. The next question is, can we trust the decision? So, can we feel confident that whatever the model will produce is trustable? You are trying to detect cancer. Can you just leave the room and let the machine actually start making decisions about whether someone has cancer or not? Is the model fair? Meaning that, does the model actually favor a particular race? You train a model using, for example, data, medical data coming only from one region in Europe. What about if I take the same model and move it across Asia? Will the model be, again, fair towards the Asian population? What are the features that are really important and contribute to a certain decision? That is actually another main question that we have to answer. There are mechanisms for inspecting actually the most influential features. And again, what happens when the model is wrong? Is it because you didn't train it correct, or is it because the data? Good? So again, these are like the different levels of explainability. So transparency is one, so look through the model, understand what the model is producing. That means that, okay, how do the neurons, for instance, activate, are active or are inactive, how they are influence each other, and how you make a decision. Trust, accountability. So accountability actually is slightly different than responsibility, because responsibility means that we are doing everything prior to building a model, but accountability is actually what happens after you build a model. Debugging, which is also really important, means that you need to have the mechanism, and when I'm talking about debugging, I'm not strictly talking about there is a code, there is an error in the code and you have to debug it. Okay, this is also really important, but even if your model is actually running pretty well, you should be able to debug its decisions. Okay, this is where we are referring to debugging in that context. Fairness and safety. Okay, safety is actually really important because it extends to privacy. So, for instance, you have dealt with LLMs. Okay, all of us have. And what happens is we can sometimes give a lot of sensitive information to the LLM. The LLM can actually train using this sensitive information and improve over time. Is that actually something credible for the system? The answer is no. Okay? So that is not safe for the system. That is not safe for the decision that will happen later on. And in the context of a single prediction, that may not be a huge issue immediately. But think that systems like this will be integrated within agents. And then now the agent will be an autonomous system that can actually make predictions, take decisions, take actions. Okay? So you don't want actually the agent make decisions or take actions using your sensitive personal data. Okay? Now the two types of explainability could be divided into two different categories. One is called the global explainability and the other is called the local explainability. The global explainability refers to feature importance, boundary decisions, model summaries. So it's more about overall. We don't really care about a single prediction made by the system. But we care, for example, how are the features ranked? What are the most important features for the whole model that has been trained using the training data? And again, global explainability is not really easy to work with when you are dealing with neural networks, but there are other models that global explainability comes for free. Can you imagine what, can you tell us one model, for example, that you may have seen in your career that is great for global explainability and feature ranking? For example, is logistic regression for free global explainable? Yes? Yes, but not directly. Okay, another one. Is decision trees global explainable? Yes. When the decision trees are made, are trained, the output is actually a feature ranking. So for the whole model, you immediately know what are the most important features. It's transparent. You can see through the model for free. But when you are working with neural networks, that's not the case anymore. Okay? You have to actually adapt. You have to use other tools to get this global explainability. Now, local explainability on the other hand is that when we are looking at very specific decisions. So you already have, let's say, documents, either translated or not, but you are making a certain decision that this document belongs to class sports. What are the most influential features from that observation that contribute to the class sports? This is what local explainability is about. Okay? So this is actually a very nice diagram, and when you are doing research and when you are actually working on real projects, I highly recommend you include it somehow. Okay? Why is that? Because you see on the y-axis we have model complexity. Model complexity means nothing but how many parameters are you training or you are estimating for your model. Okay? You already know that as we are working with more complex architectures, the parameters or the set of parameters increases. So that means that the number of parameters goes up, but on the x-axis, instead of power or accuracy or something else, you just put interpretability, not explainability, interpretability. Okay? There are particular metrics that you can use for interpretability in order to get a score, how interpretable your model is. Okay? And in this figure, what we are demonstrating is that the higher you go in complexity, which are neural networks, the lower the interpretability is. But the lower in complexity, the higher interpretability gets when you are using linear regression, decision trees, logistic regression, and so on. Good? So I highly recommend that when you are working with a model, you should sacrifice a little bit about accuracy and stay somewhere here. This straight line here is what we call the sweet spot between complexity and interpretability. Okay? You don't want to actually lose a lot of accuracy by using logistic regression or decision trees to gain interpretability, but you also don't want to lose interpretability by just gaining a lot of accuracy. Okay? Keep in mind then, again, that the sweet spot should be there, you should inspect for it, and you should present it. Very powerful plot. So, when you are working with neural networks in particular, you have something like this. All right? What does it really mean with explainability having those? Can you extract anything useful out of this? Can you actually have explainability when you are looking at this figure? The answer is no, right? It's very difficult to actually get explainable decisions by just looking at this figure. Okay? We will see today, Ogerta will go through some case studies. Where starting from this, training this network, you will be able to actually extract useful features. And in the lab as well. So when we're going to work with the CNN model, you will be able to actually take an image, see how the image evolves within this neural network, and find out what are the most important features while this network is trained. Okay, that's something we call heat maps. You will see what are the particular pixels within the image that contribute the most to a certain decision, cats versus dog. Okay? Interrupt me if you have any questions. I'm going a little fast because Ogerta has good stuff to say. Okay. So this is more of an introductory type of thing. Here, with CNNs in particular, that's what we are interested in. We are interested about the initial pixels on the left and see how those patterns actually contribute to the final decision. Remember that in the early layers, the system is learning about edges, corners, textures, and so on. This would be important for a certain decision. In the middle layers, we are learning patterns that are related to shapes, objects, and so on. And at the very end, we are eventually able to get the semantic concepts, okay, about the images that you are working or using as training data. Now again, with the heat maps, you will be able to actually identify all of those and see how they contribute towards this training. Good? The applications are many. Some of them are called are in a medical domain. Medical imaging is actually very picky with explainability because you really want to know the particular regions about, for example, the brain that are influencing a certain decision. Autonomous driving, for example, is another application that we are interested in, making certain decisions and knowing why the system or the car is turning left or right or stops. Facial recognition is another one. When you are working, let's say, or when you have built an application for an airport and you are trying to detect whether or not something is suspicious using faces, you really want to know that the system is actually making the moral decision, okay, and do not actually jail someone because of certain features of the face, okay. That actually has a very, maybe I should say, deep discussion because and it is also regional. There are certain countries in the world, and you can imagine which countries, I'm not going to say which countries, that the government actually built facial recognition systems to identify whether a person is homosexual or not. Yeah. So, it's shocking, right? As an application. But facial recognition can easily do this, by the way. If you have millions of images, you can easily actually train a CNN and make this decision. Okay? Now, you see that the question is not about how to build anymore this system. You already know how to build it. You use a CNN model with a couple of thousands of parameters and build it. But the questions are coming afterwards, the accountability that we mentioned earlier. Should you do that as a scientist? Okay? And security systems, I mean, nothing to say more than this. You already can imagine why we care about explainability in security systems. So what is the misleading information? And if we are trying to make a prediction, say for example, we have the image on the left and you are trying to predict that the object is a wolf, okay? The CNN can take this as an input and get out the output which is wolf, yes or no, okay? Say that the model is actually making the correct prediction, wolf, with high confidence. Should we still trust the system? The answer is no. What we really need to do is to actually add a layer, another tool on the top of your CNN and really get those regions and see what are the regions that mostly influence the decision. Something on the right is what your new tool will display for you. It could segment, for example, the area of the wolf, okay, and it will tell you that the wolf is not really important for that decision. And it can actually highlight the background. So immediately in that case, even if your accuracy is very high, you can safely say that the system needs to be tuned again or debugged again because it is not taking into account the right regions of an image when it's making a decision. Question for you, and question to think about. Say that I'm having a CNN model that I trained pretty well and gives me high accuracy. However, there are, out of, let's say, 1,000 decisions that are made, 100 decisions are wrong in explainability, are wrong in the interpretability. I'm getting off particular regions. Would I still take this model into production? Would I still take the model, integrate it into a system, and then deploy? So the system should be about, let's say, I don't know, agent. Is an agent and needs to make, takes other actions. But one of the components of the system is about recognition. So, but out of 1,000 decisions, 100 are invalid in explainability. Should I still take it and give it, integrate it into a system and then deploy?
Yes, with warnings.
Hmm?
Yes, you can use with some warnings.
10% of the time, very good, yeah. 10% of the time, your system is actually predicting something correct, but with the wrong reason. But using the wrong reason. Should you still give it for deployment? Or should you integrate it and then deploy?
Depends on the application. If it is, for example, medical, it is dangerous. If it is something...
It depends on the application. If it is medical, it's dangerous, right? So you don't even want a single case that someone has cancer and you detect not, or the other way around. Okay? I should say, from my own experience, that no matter what, even if you have a 10%, that is a very high percentage, by the way. You shouldn't deploy. You shouldn't integrate. You should go back and sacrifice accuracy to get better interpretability. Okay? And from my perspective, I would say no matter what the application is, you shouldn't trust a system that is 10% inaccurate or unexplainable. Good? Simple reason is because when a little model is integrated within a system and then the system deploys, think that more data are coming in. Think that this is gonna scale up eventually. The 10% will easily become 50%. And you don't want to actually deploy something that will scale up quickly. Explainability is something that is so sensitive in the parameters. It can scale up easily and give wrong predictions. Not wrong in accuracy, but wrong in explainability. So you always have to think and go back.
What if it will be like 1%, 2%? When we are working with images...
Even that actually is dangerous.
We are working with images, 90% security is...
That's a great point. So let me repeat what you said. If we are working with images and less security, okay, 10% is fine. Okay, I agree. But do I really need something there? So say that at the end of the day, I train the model, I integrate the model into a system, the system is deployed, and I'm getting, let's say, this 10% of non-explainable cases. What should happen there? There is something really important that I should include in my final system. It's the human in the loop. We haven't talked about human in the loop. We are still thinking that everything should be autonomous. But that's not the case. There should always be a human in the loop. Medical domains.
Warning system and then let's go forward.
Exactly. Medical domains, for example, the doctor should actually, even if we see, the doctor should actually inspect the result. Okay? And there is something very cool in deep learning, machine learning, in the machine learning field, that the human in the loop is not just a passive user. It's not just inspecting there, sitting in the chair and inspecting whether or not a machine. So the human in the loop can actually inform the system and improve the system over time. How can that happen? For example, a system that is making a certain decision about, let's say, cancer, yes or no, can ask also the doctor, can you give me, or can you highlight in the area by just clicking at the region of the image, what do you think are the important features that contribute to your decision? Not the machine's decision, but to a human decision. Now, the features are getting some scores, and those scores are going back to the system, and the system retrains. Not only by using the feature importance from the explainability tools, but also from the human scoring. Okay? That is actually the human in the loop, and it's in an active manner. So that will even further improve the system. Good? Okay, so Gerda will talk about this in more detail, but one of the tools that can actually provide local explainability for certain decisions, and this is something that you also have in your lab and project, is LIME. Okay? LIME is one of the tools developed earlier 2020s. So I have a particular decision. I would like to get the sentiment out of it, positive or negative. The film was emotional, powerful, and beautifully written. Okay? As a human, we immediately see that this has a positive sentiment, right? But the machine can also predict that. However, as a human, we may have a reasoning behind our decision. We can easily say here that the word powerful and beautifully, probably in our mind, contribute mostly to the decision made positive sentiment. Now, what we want to see here is that the system also aligns with human intuition, with your intuition. And Line provides this. So Line, as a tool, can extract the words emotional, powerful, beautifully, and can give scores to the importance of those words in a certain decision, positive or negative. Here what you see, for example, is with blue could be towards negative, the negative class, but with yellow could be towards the positive class. All right? From there, as a human, as a scientist, you can extract this output from the Line tool, and you can even go further. Okay? Questions on this? SHAP is another tool. It's based on, the underlying mechanism of SHAP. It's based on some ideas from game theory, but overall it does most likely what Line does. It gives you, or it provides to you, the importance of particular words within a single prediction. Okay? Attention is another nice visualization tool. So remember, I think it was either yesterday or the day before when we talked about attention and transformers. 2017, attention was something big that changed the world in LLMs. Okay? That was a nice deep neural network idea that people used in order to improve the GPT models. And in natural language processing, for example, you can find out what are the important words about the quick brown fox jumps over the lame dog. That's just simply one observation. Okay? You can even find out how each word can influence the other words towards a certain decision. And in vision, in computer vision applications, you can even get and highlight particular regions about an image and find out how they influence a certain decision. Okay? So, the next big thing is bias. So, we talked about explainability, but bias is another big area that we have to pay extra attention. Not only when you are explaining, but when you are preparing your data, before your model is even made. You see that there is a big funnel there that gets the data into. The data can come from anywhere, could be of any modality. But if there are biases within the data, and they get into the system, the model can magnify those biases, and your decisions can be magnified as well. Now, the different types of biases within the data are like unbalances, that you have certain attributes that you have a majority. For example, you may have more data that are coming from a certain gender. You would expect that if this is the case, then your final decisions will be biased towards a certain gender. Okay? Annotation biases. This is something else that is really important. Even if I have a balanced data set, I have, let's say, 2 labels, and I know that each label contains the same amount, and all the attributes, even if there are all the attributes are also balanced, gender, race, and so on. The annotation is something really important. Who is doing the annotation? If you are working with social media, okay, and you would like to detect misinformation, for example, you need a training data set that contains reliable, let's say, social media posts and misinformation social media posts. Okay, take me as one of the people who are going to annotate misinformation, and take Ogerta as the other person who is going to annotate manually misinformation. Question for you. Do you think that me and Ogerta will 100% agree on our decisions? No. Right? Culturally, background-wise, educationally, and so on and so forth, we will disagree. Okay? You already see the annotation bias here. Because if we do not take an extra step on this process where we are annotating, the two of us, that actually will include a data set, a training data set that has biases on the annotation. Okay? And to give you a little bit of a true story, in 2020, I worked on a project. I still work on a project, but I worked on a project that was detecting misinformation on social media posts. That was back then was tweets during coronavirus. Okay, and the task was that I wanted to train a machine to actually detect whether or not a particular tweet is about misinformation regarding coronavirus. The problem immediately was that when we wanted to train a model, we needed a data set. That was the easy part, because we had a partner in Canada who is actually a specialist in social media, and he extracted a couple of millions of tweets with particular keywords about coronavirus and so on, and provided them to us. What was missing was the labels. We didn't really know whether a tweet is labeled as misinformation or not. So we said, okay, from these millions of data, we want to extract a couple of tweets and start ranking them manually as misinformation or not. Okay, challenge number 2. What is misinformation?
Something that is not true, or something that is half true.
So one answer is having the wrong information.
Something that is not true, or is not based on facts.
Something that is not true is not based on facts.
Real or fake?
Okay, good. Fake or not?
Take on label just to say if it is true or false or
Okay, so you see that immediately the answers are like true or false, fake or not.
Binary classification.
It's a binary classification problem, but this is what we actually say as humans or as scientists. I actually had to partner with someone who is from a sociolinguistic field. So misinformation was distinguished by fake news. Misinformation is not fake news. Misinformation is not disinformation. Misinformation is not propaganda. Misinformation is not unreliable information. Misinformation is not false facts. From a social science perspective, all of those terms that I just explained have a particular definition. And if you go to the library here and open a social science book and look for the definition of propaganda, you will actually find a very two-line definition. Okay? So, what we did in order to actually tackle this issue was that she sat down and she came up with a framework of what misinformation is about, and she even highlighted particular words about misinformation, rules about misinformation. So it was a human rule-based system that she came up with. So it was a one-page document with all the different definitions, rules, and so on. And this was the basis for us to start actually labeling, annotating. Okay, listen to the interesting story. We both took actually this framework, we distributed it across 5 people, and we start making annotations. after, let's say, 7 hours, each of us had labeled around 1,000 tweets. Okay, the next step, or in Africa, training an LLM. So would the data center that we are building next to Nigeria will consume all of the energy than the whole Nigeria just to train a model to do facial recognition? Is this moral to happen? That is actually a difficult question to answer. We don't have to answer yes or no. But these are aspects that Green AI is dealing with. And not only this, not only from a qualitative perspective, but also from a quantitative perspective. There are now nice tools, and if you Google and you see, and I haven't included here, but you can Google and find them easily. You can, while you are training a model, even the baby models that we have trained here, the CNNs, the RNNs, you can at the same time add another layer, and it's called the carbon footprint. At the same time, with your hardware, you can monitor how much carbon footprint you are producing. Okay? And then you can actually have those type of plots where I get a lot of accuracy with millions of parameters, but I spend a lot of energy for that, and so on. I'm gonna stop here because I would like Gerta to go over. These are just a couple of slides that we already talked, but I think she has more details to
Case
share.
study, yeah. I have a case study with summary of data to share.
Nice. Any questions? No? While Gerta is setting up in the Google Classroom, I have there are a couple of slides also from our book on machine learning evaluation, and there is a chapter there, chapter 11, that you can go through and read all of the different principles and how to use quantitative ways to measure for fairness, representation, Green AI, and so on. Okay. Good.
Okay, so mathematicians build this kind of models, but our part is applied AI and scientists and so on. We want to test with real data sets in order to trust or not, or to find problems. And this is what I'm doing today. So I bring here research that I have done with bachelor students in terms of how we can not build, but let's check about responsible AI elements and aspects in face news detection, and it will be a comparison study in terms of accuracy, how can we generalize the findings and so on, and talk about and tackle the aspects about explainability. First of all, what is fake news detection? So I'm not talking about misinformation, because he went through linguistic issue and so on. I make a very short and very simple definitions about fake news detection. If we want to build up a system that is going to detect some articles or some news that we are processing, we need to build up a classifier. In this example, it will be a binary classifier that we want to classify all the articles that we have into two classes. One, it will be the fake, and the other one, it will be the real one. How to do it? There are different approaches of dealing with this, starting from the simplest one, that it is based on the content. And when we talk about content, you have textual data. We are going to process based on the content of the text that you have. And what we are looking in that, we can do analysis in terms of vocabulary that we have in our articles or in the data set, about the style. We can be focused on sentiment analysis, positive, negative, neutral, and so on, sarcastic tone that you can find there. But this is the easiest one, and it's the easiest approach because it's also reproducible. In terms of the second one, which is social context. What? As we are talking about fake news, we know that it's important also how the news are spread and so on. And when we talk about social context, I'm bringing it, for example, social media aspects and elements where we can spread all this fake news and so on. And in the social context, we want to check about how the information is spread and the actors that spread this information. So now I'm talking about some more advanced techniques when we build up some knowledge graph, we call it, that are based on the graph theory, where all the actors in a network, because these are people that are communicating and spreading all this news and so on, they will be the nodes of the graph, and after that there will be connections between them and so on, and we build up a knowledge graph usually based on the architecture that we build. We also create some ontologies, knowledge graph, we link together and so on. The other one is evidence hour. What does that mean? You have some textual data, some articles that you want to check and to classify if they are fake or if they are real, and rather than using and base your judgment only on the data set that you have, the article itself, you are going now to check in other sources in order to figure out in a proper way if this is a fake or if this is a news. So in order to do it, rather than considering and based all the analysis on your data set that you have, on the articles that you want to classify, you are getting some additional data sources now, so you have more than one source in order to verify the facts and what it is written in the text that you are processing. The last one is about multimodal, which is a more complex process to go through, where you have to combine images, video, metadata, and so on, but this is harder task. In the experiments that I'm going to share with you today and go through, the focus is to show to you that usually it's not the accuracy that matters, and the accuracy is not enough. Let's say we start with building up and training some models in order to have a good accuracy, but that's not enough because we have to consider all the other elements in terms of bias, explainability, and fairness, and so on. We'll focus on the content-based. So content-based detection, because this is also something with a basic approach, but we'll base our analysis not on multiple fact-checking on other data sources and so on. There will be two different data sets in terms of not only being different of the number of the records that they have, but also being different in the structure of the data set in order to show to you that you can run a logistic regression model that you can get in one data set an accuracy of 98%. But if I'm using another data set that it's different in terms of the structure, not only in terms of the total number of records, but in the structure and in the content, so I can end up with an accuracy that it goes to 40%. So does that mean that the model is not good or not? See, these kind of things. So now, why we're having this here and in terms of how it matters to in the context of responsible AI. The first one that we have been talking during all this course, it's about the generalization problem. A model can be trained on political news, but might fail on another data set that might be in terms of health information and so on. There is the black box problem, so we know now that in terms of the deep learning, at least, because we saw a graph that Zoe were showing before as we are working with neural networks, let's say, so the complexity increase, but interoperability decrease as well. So we less understand what this model do, and also think about different neural networks with so many layers in between. We don't know exactly or keep audit and understand about how the information is transferred from one layer to another. What we receive at the end is the output that we get in that last layer, dense layer, if you go back to the architecture and so on. And this is where we want to see that kind of black box in here. And the third one is about the fairness problem. So what happens? In the first one, you see by the experiments that I have been using two different data sets. One is from Google, and in one of them with the same model, the accuracy that we will achieve is 90%, with the other one is 46%. Does accuracy is enough? So should I say that I have built up a very good predictive model, classification model that is going to classify my articles into fake and real ones? No, because I'm testing in another data set and the accuracy will be dropped from 90% you'll see to 49 in another data set. So that model itself is not good enough in order to do the fake detection. So that's not a good model. In terms of the black box, why this article is flat these are the questions that I want to address. Why this article is flat as fake? What is the topic, the author, the style? So I want to understand now. There is an article about Obama. He's talking about terrorism and mosque and so on. And that is classified as a fake one. But in reality, that is not a fake article. It's a real one, let's say. And I want to know why the model classified like that, which is misclassification in this example. In the fairness problem now, the same example that I'm bringing with Obama, his article is about terrorism and having that regional context and so on. So it goes to fake class rather than the real class. And this happens because there is bias in my data. So I'm discovering that there are some bias in my data, and I have to think about how to mitigate this bias and so on. So let's move now in the research questions, what we have been addressing. The first one is about, this is one, and this is something that everyone does. So we want to build up a classifier. Now, which of these different models that exist, it can be traditional ones, it can be neural networks and so on, which of them is outperforming the other. So I want to find a good model in terms of doing the classification. What we do, we get the data set, we run different models, we get the evaluation metrics. Usually we can compare, we'll see via the accuracy, or we can use other evaluation metrics such as F1 and so on, and we can conclude among all these models that have been running, this is the best one. So this is the first research question about which model achieved the strongest classification performance. And the focus in here is in comparison between traditional models, because you see that 4 of the models that we have tested are from traditional machine learning, and there is another one that we have been using, which is distinct paired. The second research question that we want to address is generalization. Can I generalize by findings? What does that mean? Now, how does the performance of my classifier? So I have 5 classifiers. One of them is the best, but now I want to go further and to analyze how does the performance change if I change the structure of the data. So I'm just using the same architecture. I'm not changing anything in the model at all, but I'm just feeding new data into my model, and I want to see, in order to generalize, is my model stable, or has been just the learning from the patterns of the data that I trained, and it cannot be generalized using another data set with the same model. And the other one is research question 3, it's about explainability. When we look inside the models, I want now to use some tools, and we'll see some experiments and output that we get from using Lime and Sharp that Zoe's mentioned, in order to see why some of my records are correctly classified. I want to understand, but I'm also going to look at some records that they are wrongly classified in order to understand why they are wrongly classified. And this is where we have what we call it human in the loop. I'm running this Lime and Sharp as toolkit, let's say. I'm getting some output, but the judgment is done by the humans, because I have to understand why the model has taken that kind of decision. So this is where the human in the loop element appears. The last one is about getting all these kind of main pillars of what we call responsible AI, because we have fairness, we have generalization, we want to have models that their performance is good and so on. And in this example, I want to answer, is this data set and all the models that I've building or deploying good enough in order to cover all the main pillars of what are under responsible AI? So this will be the last research questions. Let's now have a quick look about the models that have been introduced. The first one is the Lime, and it is the simplest one, but they have a main difference with the Sharp one. The Lime one stands for local interpretable model. So what does that mean? What that local means? So it means that if I use this as a toolkit, we call this toolkit, what I can get? I want to understand for a specific record, for a specific article, why it is classified as fake or news. So I can do this kind of analysis and explore at an instance level. When I say instance level local, it means for one instance. Okay? When it comes to the other toolkit, which is Sharp, and it stands for Sharply, this is based on game theory that we say. It calculates by looking at every possible combinations of features. So now the other one, the Sharp itself, is not looking at local instances, but is providing to me some evidences about the overall model. So this is a big difference. So the other one is looking locally, the other one is looking globally for the whole model. Okay? And now here we will best which of these two toolkits we have to use. Let's say Line is easier, and if we want to go and check individual records about why they are classified to a specific class and to the other one, so we go for line. If we want to get an overall overview about the model itself in a global level, so we are going to use sharp. In these experiments, I have been using both of them. But let's have a look to the data set first. What data set we have been using? We have been using two data sets. They are supervised, so no need to do to classify, to go, let's say, and do manually labeling of the data and so on. The first data set comes from Kaggle, fake and real news there, and they are at article level. It's a balanced, almost balanced data set where we have in total around 44,000 records, and 23,000 of these records, they belong to the fake class, and 21,000 they belong to the real article, let's say. Also, when you process this textual data, I want to understand the average length of my articles, because why I'm doing it. I have to explore the data set, but also I have to figure out why, where I'm using the other data set, I will see a drop in my accuracy or in the evaluation metrics. And one of the reasons, it might be to the different nature of, or to the different structure of the data set itself. So now my data set from Kaggle, the average length is 438 words in each article, okay? Do you have any question for the first data set? Now, the other data set, which is different from that one, text again, so it's liar, it's from political facts, and it claims level the classification here. In total, I have around 12,000 total claims there, and I have been using to train 10,000 of them, and you see that there is a difference in terms of the average. I have only 18 words, so it means that they are short articles, or short political facts rather than articles, in comparison to the Kaggle one. And in the data set, we have 6 labels, but we have been pre-processing it in order to go for a binary classification. So these are the two data sets that we have been using in our experiments. Now, the methodology. It's a pipeline, straightforward pipeline, similar to all the experiments that we have been doing in all the exercises. So data collection, 2 different data sets, one from Kaggle and the other ER. Pre-processing. Now, in terms of the pre-processing, textual data, we have been talking about that, but I included a slide in order to explain in the next slide about TF-IDF. So now, we know that the machine understands only numeric values, so we need to apply some feature extraction techniques in order to convert this textual data that we have into numerical values. And in this example, we have been using TF-IDF for what? You see the models here. Naive Bayes, logistic regression, linear support vector machine, random forest. Traditional machine learning models. And there is another one now that we are expecting to get better results, okay, in comparison to the traditional methods, which is distinct, which is based on the transformer that we have been talking and introducing a bit yesterday to you. Why we have selected, we can try also other models, but there are so many models around, and when we want to select the models that we want to test and to compare and so on, there might be some reasons. We consider their feature representation. All these first 4, we have been applying, they work with TF-IDF, so you have to convert now the text in the numerical matrix, TF-IDF, and there is the architecture there, and there are some reasons why we have selected these models. The last one is this invert, is the transformer here, and the architecture is fine-tuned on labeled data, but the main difference now that we want to compare is because, you see, the first 4, they are traditional ones. When it comes to the capturing the context hour, this happens to the last one, which is the distilled back. Now, in terms of the methodology, we pre-process it, and after we pre-process, we are going to do the training. We are going to evaluate the performance. We want to see if we can generalize in order to answer to the second research questions. And the last one is about, let's have a look to explainability. Let's apply these 2 toolkits, the line and sharp, and see what we can get in order to better understand the behavior of the model and what is going in the black box of our models and so on. So in terms of the feature extraction, what is that TF-IDF? We mentioned yesterday that the easiest way in order to deal with feature extraction in textual data, in NLP, what we do, we can go from the bag of words method.
So we list all the words that we have in the document, we count their frequency, and we create a matrix. So this is the first one. But it has some drawbacks. And one of the drawbacks that we talked yesterday is about having a sparse matrix. It will be a very big matrix, but for example, my name, Ogerta, in that huge corpus or documents, it appears only one. And there will be so many rows and columns in the matrix, so it's 0. So this is the sparse one. Second is about the importance of the word. I brought yesterday an example about the hotel. If I'm processing some data related to the hotel is good, the hotel is brilliant, the hotel was not good, and so on. The word hotel itself has the highest frequency. It will be dominant, it will play an important role when I'm going to train the model and so on. But in my data set, in my context, it's not getting any signal, because I know that I'm processing data related to the hotel. So that is why I want to now deal with these two drawbacks that it comes from the bag of words as a simple method for feature extraction. And there is another one that is a TF-IDF, and I'm quite sure everyone can easily understand because there is a mathematical formula behind it about how to calculate this TF-IDF. It contains two parts that we have to multiply. The first one is about term frequency. How we can calculate the term frequency? It will be, we count how many times a term appears in a document, okay? And we divide by the total terms in the document. So a document has 100 words. The word hotel appears 3 times, 3 divided by 100. Okay, so this is the term frequency. Now, we calculate the inverse document frequency, and this is a combination we have to multiply now. For each of the cells that we are having in the matrix now, there will be a multiplication of these two values. The other one, the inverse document frequency, how it is calculated. This is very important, and why we are including it. We are including the second component in that multiplication because we want to deal with the second drawback. So I want now that rare words to appear, okay? Because for me it was not important the word hotel. It appears 3, 4, 100 times. But that's not, I want to capture the rare words because they bring signals in my analysis and so on. And how this happens? How rare is the word across all documents? In order to do it now, there is a formula of how to calculate the inverse document frequency here, and it will be equal to the log now of n. N is the total number of documents that I have, how many articles I have, 100, 200, and so on, divided by now the frequency that term appears in the document, not about frequency. If it appears in the first document, in the second document, in the third document, 3 times. So it will be log of 1,000 documents divided by 3. Okay? And now if I multiply these two, this is where it comes the TF-IDF. And the high score there, for me now means that frequent here, rare anywhere. So it's frequent here, it's rare anywhere. So it means that it might contain meaningful sign. So that is important about that. Because the simplest approach of bag of words, when we consider only the frequency, it contains a drawback about rare, and we want to capture this kind of meaningful signs everywhere. So this is the feature extraction that we have been using with traditional methods in here. In terms of the transformer, we started to talk about BERT in 2018, and after that there has been progress in bringing up other models and so on, because this is how it works. We come up with a model, we see that it has some drawbacks, limitations, maybe they are powerful, but they are complex and so on, and there are other models coming up. The first one, BERT in 2018, 110 million parameters, very complex one. It is based on the bidirectional transformer now, and why they become powerful in 2018. Always I mentioned, due to the training. It has been trained on a very large corpus of data coming from Wikipedia, books, and so on. After that, scientists has been thinking about, okay, very complex, time consuming in terms of training, computational power, and so on, and due to limitation in resources. So they try another technique, which is knowledge distillation. So in terms of knowledge distillation, is the concept of teacher and student now. What we want to do here? So rather than testing everything on the teacher itself, we now create a very simple model as a student. Let's say we try to learn from them and we want to adapt it to the teacher and one. This is where it comes the knowledge distillation in here. And why that's good? Because now we are removing 40% of the parameters. So in terms of the complexity, we decrease the complexity, so we are having less parameters with the knowledge distillation. So it's like what we are doing here, just reducing the complexity, but also we try to keep accuracy. And what happens? We removed 40% of the parameters from the pair, but we retain 97% of that performance. So still they are really good. And also we are doing some research and some architecture and so on in terms of how this knowledge distillation might be used in knowledge graphs and so on. Because also knowledge graphs are very computational. In terms of after knowledge graph, we have distill BERT, which are a bit simplified version in distill. BERT, 66 million parameters, 6 layers. They are faster due to also having less parameters, so they make it faster and so on, but still they are contextually aware. And the last one is about fine-tuning. Fine-tuning are the models that rather than doing the training process, we are using some models that they are pre-trained, okay? So there is no need to go through the learning process, all this process of updating the weights and so on until we achieve the minimum level loss function, what we have been talking about. But we are using some models that they are pre-trained on a very large corpus of data, and we are just putting our data sets there, our records into there, and the model is doing the prediction or the classification itself. So we are getting the output from the model, okay? So it's like having the dense layer at the end where we get the output and so on. So now in this experiment we have been using distill BERT. In terms of the first research question, the first research question was about accuracy now. Which of this model is outperforming and so on. So we see here that the distill BERT is getting the highest one. 99.96%. Everyone might be, oh, this is the best. We have a very good model in order to do the classification in fake and real and so on, because it's almost 100%, yeah? So everyone might be happy with that. The other one, linear support vector machine, is also achieving a good performance in here. It's 99.31. And there are others that you can see random forest and so on. Okay, good accuracy. Now, let me go and have a look to can I have an answer? What are these figures in here? I have it in the title, okay, confusion matrix. Okay, so these are confusion matrix now. I want to see how good my models are, but I have to check if I have true positive, true negative, false positive, false negative. This is what the confusion matrix brings in here. Okay, the best one, it was that distill BERT, yeah? I should be satisfied with that one, but do you see something that, you know, can draw your attention in this confusion matrix? What happens in here? So the distill BERT, yeah, is the powerful one, transformers and so on, 99 point something accuracy. But if I go and check on the confusion matrix, false negative, 0. And in terms of false positive, 2. So let's say it makes sense because it's almost 100%. Should I trust it? So this is the question now. Should I trust these results? I'm getting, you see now, only 2 errors. That they go to the false positive class, so, and 0 in false negative from that one. So 0 false positive. Every fake articles has been detected. So do I have overfitting? All models looks very impressive in here. But now what I have to do, I have to move down to the second research questions. And what I'm doing, I'm testing the same one. I'm not changing anything in the model itself, but let's see now with another data set that is different in structure and see what kind of results I'm getting in order to generalize the findings. So I cannot generalize and say this is a good model. If you use, I cannot say to you right now that, oh everyone, if you go home and if you use distill BERT, and I can provide you the architecture as well, so you are getting almost 100% accuracy and you will not get any false negative and so on. Can I say this to you? No. In order to generalize and to say, I can, but in order to generalize and so on, I need to do some other tests. But before we are going to that one, I wanted to check first, before going to the second questions about testing with another data set, I wanted to check about the model consistency, about the split. Someone might say, okay, how did you split the data? So there was a split in the data, maybe there was somewhere, but I didn't mention. Okay, let me go. So how we split the data? 70% for training, 15% for validation, and 50% for testing. So now we want just to check the model consistency in terms of the split. We run the same models, a very simple task. Let's say we have just changed the random seed to different values and so on in order to see is the model stable or not, let's say, or it depends on the training itself because they are randomly assigned and so on. As you can see here, for all of them, let's say naive bias, logistic regression, linear supervisor machine, and random forest, all of them, let's say, the curve is almost flat. So saying that, it doesn't have any impact, let's say, at all. So this is just to confirm, or even the variance that I get, so it's very low, less than 1 point decrease or increase in the variance, which show to me that these results are stable. They are not of being lucky due to what records has been used for training and so on. Now, the generalization problem here. A model is going to be generalized if it can perform well on data from a different distribution than its training set. Because you have training, you train on the model, but the model now it will be good and you can generalize if it's going to perform well on some other or different distribution of the data, let's say. And this is a central challenge in deploying NLP models in real world conditions. So now, what I'm doing? For training, you see I'm using the Kaggle one, the data set with articles, with long articles, with the average was 400 and something words per article, okay? So they are, the source is various online media text, full article, and what I have, headline and body of the article that I have been processed, and vocabulary is formal and informal. And fake silliness exists there in terms of the emotional tone and so on. When it comes to the other one, what I'm doing now, I'm training on this Kaggle, but I'm testing on another one. You understand what I'm saying? So the training happens on Kaggle, the testing happens on another data set now. And the second one is about liar, which is a short political claim, 18 words average each of them. And I'm just checking the performance in here in order, because what I do for generalization, I'm doing a domain shift now, you see? So I'm shifting now because this is different vocabulary style, length, topic distribution, because these are political articles, there are political facts, okay? And now the second one is about task difficulty. I'm checking also task difficulty. Why? Because the Kaggle one has long articles. When it comes to the other one, I'm having short claims that are harder to classify than long articles. Because in short claims it's more difficult in order to, you have less context than in the longer ones. So this is what we are doing in here. And let's have a look now, see. I'm testing the same model that has been trained on the Kaggle, and what is the result that I can get with the LDR ones. So you see a drop now. So naive bias was 95%, and now it goes to 49, 58, 59, 61, and so on. So I cannot generalize now.
What is the meaning of red bars?
You see here, the blue one is the Kaggle.
It's not visible.
It's not visible, yeah. The blue one in here are the first data set, the Kaggle one. That big data set.
Okay.
The other one is using that LIAR,
Yes.
political fact.
The
Okay?
F1 score, I don't know if
F1.
No, it's asking about the colors of the line.
the color?
Yes.
Yes. In terms of the, it's in here, but I skipped it because probably all of you know. Sometimes we talk about comparing models based on the accuracy, how many records are correctly classified, let's say. Based on the confusion matrix, so these two, they are correctly classified. They are positive, classified as positive, true positive. True negative, negative, negative. The errors happens in this diagonal in here, where we have false negative and false positive. There are different evaluation metrics that you can compare the models, but also related. Let's say high accuracy, if you compare by accuracy, is the same if you compare also based on the FN and so on. So F1 score here, it will be, this is the formula of calculating the F1 score. It will be 2 multiplied by precision and recall divided by precision plus recall. But what is precision now? Is true positive divided by true positive plus false positive, and recall is true positive divided by true positive plus false negative. If you want, you can explore it later on. Now, you see that in order to generalize, now we are doing cross data evaluation in here. So in here we see that there is Now, a huge drop, let's say, in terms of the evaluation metrics, and in this example is F1, but the same, it might be if we report it based on the accuracy. Yeah, so what I'm doing now, I'm using the same data set, liar now. So in the first one example, I trained my model with Kaggle. I tested my model with another data set that has not seen the model itself. Now what I'm doing, I figure out that this model cannot be generalized because if I use another data set, so I cannot get good performance from the model and so on. I'm using now the data set LR as a baseline in order to separate the main sheet from task difficulty. Why? Because what? Someone might say, okay, you are testing it, but maybe this is due to the structure of the data, or I want to understand, is it due to the nature of the model itself? It's difficult to find a good classifier based on the nature of the data, or it comes because it's due to the previous model. So in order now to split the two main aspects, because one it was about the data itself and the other it was about the domain, so I'm running now only on that specific data set now. So I'm using the LR in order to separate domain sheet from task difficulty here. And what I'm getting, still the accuracy is not high. So I'm not merging now, you know. So I'm just using the one data set. I try to make a classifier with that data set. I split that into training, testing. I run the training, I'm doing the testing with the same data set. Still, this is not, still using that one, I'm not getting high results. So even the highest accuracy, if we can see here, it goes, the best accuracy that I can achieve is 60.77 in here. So what does that mean? This is a data set that it is harder. It's not about just being different now, but this is a harder data set, and one of the things that this is harder to be correctly classified and so on, it might be due to the fact that the structure of the data itself, but also the very short sentences or claims and so on. Now, here, there is a comparison between all of these models, NilePy, logistic regression, linear support vector, machine random forest, and distinct pair that we achieve 99.96%. If you see, we have not done some of the calculations and so on due to not having resources in place to run all these things. Now, what we are doing, okay, they are not performing well, I cannot generalize. I have to go next now to explore why and to understand what happens with the models itself, what they are doing, let's say. And this is where we come. Let's open the black box now and let's talk about the third research question that is about explainability. And we have been looking at some logistic regression features in here. From the Kaggle train, what are the top features that we get based also on the score here? Concluding, destroy America, command chief, Democrats media, budget million, advisor wide, capital management. So these are the top fake features that we get now. And now, if I go on to the other data sets, I get Obamacare, Wisconsin, Obama, rep, illegals, away, government, and so on. If you see now, the two data sets of the top fake features, they have zero overlapping. So I don't see any overlapping at all in there. So zero overlapping between both top 20 feature sets. Here I have only included some of the features, but we have done it for filtering out the top 20 feature sets and so on. So same task, same model, okay? Completely different patterns. So what happens in here? So I'm having the same task, same model, but completely different patterns that I can identify. So here there is a clear evidence of dataset artifact learning now. So how the model is learning for the dataset artifacts and so on. Now, correlation versus understanding is the core in explainable AI distinction. So what happens? The most important concept is that when we build a model here that achieves high accuracy, we have to think about, does it come because it learned from a statistical correlation there, or that not always is part of a meaningful concept. So what we have to look now, we have to think about what correlation looks like, and let's see about what understanding looks like. There are two different things, correlation and understanding itself. Okay? In terms of the correlation, I see that the word correlation, if the word Reuters appears in my articles, okay, it was classified as real. Okay? In this example, publisher brand names associated with truth, let's say, works in training but fails when Reuters is absent. So if Reuters is not there, so it will be classified as a fake, some of them. So this is a learning from correlation. Concluding, if the word concluding, it was one of the words with the highest score in the features that we have been looking at, it is associated with fake. Unusual words appear more in fake articles in this data set, okay? Wednesday, also, I figured out that there were some words, let's say, such as daily, day of week terms reflects publication timing, poor data set artifacts, completely content-free in this example, and Obama is fake because it was appearing in so many fake articles now, and that is that where Obama was there, it was classified as a fake one rather than sometimes it was not fake at all, and this is about what correlation looks like. When it comes to what understanding would look like, and we want to go for understanding, so phrases reported or some say without named attribution has to sign or settle, or it has to be considered as fabricated. Okay, so this is, I'm talking about understanding now, not only simple correlations. Now, emotional amplification. Here, there might be missing attribution that I have to check. What does it mean about missing attribution? Real name sources that might be missing there and that they have to be classified or belong to the class fake and so on. And also internal inconsistency. The real articles, they have consistent facts. Fake articles often contradict themselves across sentences that we have and so on. So this is the first one. Now, in order to look now, we are using the two toolkits that Zoe's introduced about the shape and line now in order to see how this picture looks like. So these are two toolkits that we are using and to check about if the model is correlating or is not understanding and so on. So this is something that we have to have a look into that. In terms of the top, now in the first one, here I have applied, based on the data set, in the data set that I explained to you, I have applied the sharp analysis here. What does sharp say? The words with a high score is set, video, Reuters, Hillary, Trump, Obama, Republican, Washington, Reuters, Washington, image, and so on. So this is what I get from that. But as I mentioned at the beginning, so this is not something as I mentioned, this is human in the loop now. So it's not that you get the output, even if you try to use this toolkit like sharp and line and so on. So you get some output and it's done. This is where human in the loop should stay, and you have to understand what happens and so on. So let's have a look here. Set. This is the most one with the highest score in here that we get. It's most influential attribution language because one genuine signing in the model, let's say. So if we have that word included there, it comes with 0.416, so it means that it will be a legitimate. Now, publisher brands your name. Model grants credibility if we have some publisher names, and we see here that we have some publisher names as well, like Reuters and so on. And in terms of poor artifact, day of week publication time, so there will be a day like Wednesday that I mentioned in the previous one. So if we see that one in here, day of week publication time, is completely meaningless as a signal in here in order to classify our records into being a fake or into being a real one and so on. So this is the analysis that we have to be based on the features that we get from the sharp one. Now, line. So make the difference, as we were saying. In here, in the sharp analysis, we are getting features for the overall. When we go now to the line one, the other one, which is local one, so this is global one, so I'm talking globally now about the features and so on that I have to analyze. When we go to the other one, which is a line now, and there is some results that we get from the line analysis using the data set of Kaggle. So in this one, here, it's local, so it means that for every instance that I want to do the classification to fake or to real one, so I have to go and check why this is classified as fake or why this is classified as a real one. Let's take the first one, which, we have 4 different scenarios that it might happen based on the results. The first one is the correct fake. So it's a fake article about Trump campaign. It's correctly predicted as fake, and the predictions here is 0.91, but let's look at the keywords in here that it is correctly classified as a fake one. So it's Trump, Hillary, watch, image, and video. This is what line brings as an output to you. correct result, but based on topic association in here. So I cannot make any correlation. So in here, what happens? There are some correlations that we can see, such as Trump, Hillary watching each video, but this is not understanding. The model cannot tell, as this output that I'm getting in here, the model cannot tell why the content is false. Okay? So if I go now to the other one, the real Reuters air fact incident article, it is correctly predicted as real, high probability, 0.91, but still in here, what are the keywords that it is predicted as correct real? It said Reuters, British, Police, Airport. Now, there is language and source name in here as a real classification, but if a fake article uses the same word, what it will happen? Is it going to be classified as a correct or a real? So this is what we are doing here. We are using the line, okay? You know that a specific article is classified as a real or a fake. Now I'm checking the keywords, why they are classified. Then if you don't find logic why they are classified like this, it means that the model is not good. That's what I want to say to you, that the model that I have built, it has an accuracy of 99 point or around or 100 accuracy, but it's not good enough. I cannot explain it. So that's why this doesn't make sense, okay? Because I cannot say that this is correct. I cannot conclude based on this keyword said Reuters, British, Police, Airport. This cannot be generalized, and I cannot conclude that the articles that contain these keywords, they should be classified as real rather than fake. That's what I'm saying in here. So that the data itself are not enough in order to do this kind of generalization. So this is what I can get from line if I use it. The other one, for example, is about, this is important, Obama, Muslim, American terrorist. This article now is going to be classified, if you run it, these are the keywords that you get from line. This article is going to be classified as a fake one, but this is a real one. Why it is that? This is where also we discover bias that we have been talking here. It's a fairness violation. Political sensitive terms now, such as terrorists, Muslim, and so on, they are going to predict to be considered as a fake, and this is the bias example that happens in this. The model here is going to penalize certain groups, the groups of terrorists. Okay, it's going to be like fake rather than real ones. And here is, I have to think about, I discover bias, but how can I improve the model in order to deal or to mitigate the bias that exists in my model and so on. Now, in terms of both models have the same bias and different gradunalities. Confirming here what I have to say about all these two data sets that we have been using. We were comparing logistic regression using TF-IDF, distinct BERT, where we have transformer, let's say. Saying that it doesn't mean that the best model, the more complex one like BERT, is the best one, first of all, you see. The highest accuracy is not enough, because I achieved a very high accuracy, but I cannot explain the model, why the model is behaving like that. If I test with another data set, the accuracy will be dropped to from 99 to 45, saying that that's not a good model at all, and so on. So if you see here, what we do, if we compare logistic regression with distinct BERT. The unit is individual tokens, single words that we are processing, multiple word phrases there, because we have transformer, context, hour. Granularity, word level, contextual there. Top real signal is said, Reuters, and when it comes to the other one, we get Reuters, British, Coalition, and so on. Concluding Destroy America is about top fake signals. Top fake signals on the other one are other things. False positive, Obama, Muslim, American. False positive, there are others in there one. This is where we talk about bias and so on. False negative, said Reuters, British. False negative, we don't have at all with this till BERT, zero at all. You see the confusion nothing. So comparing this to a simple traditional machine learning model with a transformer on the other part, we can conclude now that the problem here is data set driven, not architectural, because always we focus on building the most the complex architecture and so on, but sometimes the problems itself are data related rather than only on architectural part. And also, a more powerful model is not always the most trustworthy one, let's say, and we have seen that this distilled BERT with a very high accuracy, we cannot explain it and so on. In terms of explainability AI, it's very important to think about fairness, all these pillars that we mentioned in the first part of the lecture. Transparency, we need them to be transparent, and when we started to work with this kind of experiments and so on, so we have been based on NIST AI framework, which is a framework that they use in US in order to tackle the elements in terms of the responsible AI and so on. And it's important accountability, because we can't audit or change a decision that we can't see, so we have to think about these kind of black boxes and all the accountability in terms of what happens from one stage to another and so on. If we want to conclude now as a fourth research questions, it was about, let's say if we have a responsible system, because what I did, I have a data set, I build up a classifier, binary classifier. Is it responsible? Do I align with all these main pillars of responsible AI? Let's say the first one, yes, I achieved the accuracy. 100%, zero wrongly classified at all. So I achieved, let's say, the first one. It was the strongest with the data set that I, from 95 to 99 that I achieved using that BERT model. In terms of the fairness, it was not fair, because I discovered that when there were articles that they contains the word terrorism or they contains the word Obama and so on, they were misclassified as fake when they were real articles. So it was not fair, okay? In terms of generalization, I cannot generalize the model because I tested my model with two different data sets, and from 95% of accuracy, it ended up to dropped to 46, so I cannot generalize it. In terms of robustness, inability to maintain performance when we change the domain, so we move from the Kaggle to the LIAR1 where we have political facts and the structure of the data has changed and the domain has changed, so it's not robustness enough. In terms of the explainability, research question 3, so source names, layout, topics, articles that we figure out, but they do not, they were more correlation rather than having meaningful or understanding into them. So we can end up that based on the feature that has been extracted by the SHAP toolkit, but also from the line 1. So we didn't explain, so we didn't get enough evidence in order to explain that the model is performing well based on the output that I get from looking at the globally from the SHAP one with the top 20 features that we extracted, but also looking at some individual instances or articles that with line in order to understand, okay, this article is classified as a fake one, but what are the keywords used in order to classify? And there were some keywords that they were not related at all, or they didn't have any meaningful in order to make sense that, oh, based on these keywords that the model has figured out in the sentences of the specific article, he has done the classification properly, so I didn't find that kind of logic, let's say, so it was not in terms of explainability. And in terms of the transparency, so the model itself, the results that we obtain and so on, they are based and they reflect the data structure and not misinformation reasoning. So this is something that we can conclude. But think about the most important part is that the path forward, domain robust training data, it is important, but explainability, what we did, we didn't consider explainability from the beginning because we wanted to do this kind of experiments and so on. But when we build up these AI architecture systems and so on, we don't talk about explainability at the end. So we build everything and we sit and say, okay, let's test now. Do you have bias? Can we generalize and things like that? It doesn't work like that in practice. So it's not like we build and at the end we think about, okay, let's do this kind of evaluation. For sure we evaluate or improve, tune, we stay in the loop, let's say. But the problem is that when we build this kind of systems, so explainability should be a design requirement. From the moment that we start to design the system and so on, we keep in mind the principles and how to make an explainable system rather than thinking about explainability once everything is deployed and so on. And it contains some multi-domain evaluation standards and so on. So these were some experiments that I wanted to share. So if you have any questions, let me know.